Nikola Tesla is standing there with his old farmer, running his entire farm on a strange device driven by stakes in the ground. In the basement of a research facility, a relic from 1901 met the precision of 2025, and the result was chaos. What began as a harmless 10 milliwatt frequency sweep into an antique coil suddenly unleashed 2 million volts, vaporizing circuits and shutting down Google's quantum computer in the same building. A forgotten invention by Nikola Tesla, dormant for a century, had found its resonance again. It wasn't a ghost or free energy. It was physics pushed beyond control. How could a device built with hand-wound copper and cotton insulation overpower machines cooled by liquid helium? The answer shook modern science. The discovery began in March 2025, deep beneath a New York University physics building. During routine inventory work, technicians unearthed a wooden crate covered in dust and stamped with a fading label, Tesla Estate, High Voltage. Do not open. The date read 1943. Inside, wrapped in oiled canvas and thick felt, lay a copper coil taller than a man, hand-wound with ceramic insulators the size of coffee mugs and a brass nameplate etched with a single word: Wardenclyffe. The team realized instantly what they had found: one of Nikola Tesla's final resonators, a relic from his abandoned Long Island laboratory. The design matched Tesla's late-life sketches of the magnifying transmitter, a machine intended to transmit power through the Earth itself. For nearly 80 years, historians believed all surviving hardware from that era had been destroyed when the Wardenclyffe Tower was dismantled in 1917. Yet here it was untouched, a bridge between 19th-century analog genius and 21st-century digital precision. Researchers from a partnered Google Quantum Lab were called in to determine whether the coil could reveal anything about energy resonance or wireless coupling in modern systems. They expected dust and corrosion, nothing more. But as engineers unpacked their modern test gear, an Agilent N9918A FieldFox spectrum analyzer, digital oscilloscopes, and fiber optic probes, they entered unfamiliar territory. The basement still contained Tesla's original grounding rods sunk beneath the floor, old copper conductors connecting to the building's rebar. It was an environment rich with electromagnetic complexity, the kind Tesla thrived on. The engineers decided to run a low-power frequency sweep, a standard non-destructive test used for mapping resonance. At just 10 milliwatts, nothing extraordinary should have happened. It was safer than a desk lamp. Yet when the signal entered the coil's terminals, the monitors began to flicker. A strange harmonic appeared on the analyzer, an echo at 700 kilohertz, strong enough to saturate the sensors. Then, before anyone could react, the coil screamed. In the next instant, the laboratory filled with light, a phenomenon no one could explain, and a shock that would force engineers to question how an 80-year-old device could unleash the energy of a thunderstorm. The sweep lasted less than 5 seconds. At precisely 1542 Universal Time Coordinated, the output spike leapt from microvolts to megavolts. A blinding 2 million volt arc exploded from the coil's crown terminal, bridging nearly 12 feet of open air to a grounded metal shelving unit. The discharge sounded like tearing fabric magnified through a jet engine. Ozone filled the room. Every high-voltage detector on the floor tripped simultaneously as automatic sirens howled through 3 basement levels. Evacuation protocol initiated instantly. 60 personnel, technicians, grad students, and Google engineers cleared the area in 4 minutes. As they ran, emergency lights strobed crimson against the concrete walls. One researcher looked back to see the resonator still humming, a corona of blue light pulsing along its top ring even after the main power had been disconnected. The breakers had tripped. Every circuit was off. Yet the coil still drew current from where no one could tell. Security logs later confirmed the input never exceeded 0.01 watt. No hidden battery, no auxiliary feed. Whatever power had filled that coil came from resonance alone, from the environment. When the air ionized and the arc finally extinguished, silence returned to the lab except for the hiss of ventilation. There were no injuries, no fire, only disbelief. The copper windings glowed faintly, residual heat shimmering off the varnish. For hours afterward, Geiger counters registered a mild static hum, not radiation, but electromagnetic charge dissipating through the rebar-laden floor. Within a day, questions multiplied faster than answers. How could a passive device amplify a microsignal into a megavolt discharge? Was it some exotic ground loop effect? Or had the team stumbled upon Tesla's long-rumored Earth resonant principle? The engineers sealed the chamber, quarantined the coil, and began sifting through terabytes of diagnostic data. To understand what truly happened inside that room, they had to travel backward in time to the late 1890s, when a Serbian inventor first envisioned the Earth itself as part of an electrical circuit. In 1899, Nikola Tesla relocated his laboratory to Colorado Springs, chasing lightning. There, on a windswept plateau, he built a colossal coil 52 feet in diameter with a secondary winding reaching 10 meters high. He drove ground rods 200 feet into the soil and tuned his circuits until the Earth itself began to hum. His notebooks, preserved today at the Tesla Museum in Belgrade, describe standing waves of electricity coursing through the planet like the tones of a bell. When Nikola Tesla later constructed the Wardenclyffe Tower on Long Island in 1901, his dream was to broadcast wireless power across continents, electricity transmitted through both the ground and the air. Tesla's magnifying transmitter was not merely a radio, it was a resonant amplifier. The design featured two coupled coils, primary and secondary, linked through precise tuning and grounded into the planet's conductive crust. When their frequencies matched, energy could, in theory, propagate vast distances without wires. Most of these experiments ended in bankruptcy and ridicule. By 1917, the tower was demolished, and Tesla's equipment vanished into storage and estate lots. Yet a few components survived: coils, capacitors, and transformers labeled only with serial numbers and faint site tags. The rediscovered Wardenclyffe coil matched Tesla's original dimensions for his smaller prototypes: height approximately 1.88 meters, wire length around 2.5 kilometers, and resonance near 700 kilohertz. Its materials, copper windings insulated in cotton and shellac, had aged perfectly. The fact that it could still resonate so violently a century later proved Tesla's craftsmanship was not symbolic, it was functional. These were not museum curiosities. They were machines built with physical insight, principles that modern power electronics are only now beginning to rediscover. For historians, the coil's reappearance was a revelation. For engineers, it was a riddle, and perhaps a warning. Because when 21st century technology met 19th century design, something extraordinary happened. The collision of old rhythm and new precision would set the stage for the surge that followed. In 2025, the gulf between Tesla's time and ours seemed infinite. His rotary spark gaps and steam-driven alternators had long given way to silicon carbide, SiC, and gallium nitride GaN, transistors, semiconductors capable of switching at tens of megahertz with surgical precision. Yet it was precisely that precision which turned the rediscovered coil from a relic into a weapon. In the NYU Google Collaboration Lab, technicians connected a Rode and Schwartz SMB 100A signal generator to the coil's input terminals. The system could sweep through 1 million frequencies in less than 30 seconds, mapping impedance curves faster than any human could turn a dial. An AI-driven testing suite handled the sweep automatically, searching for resonance peaks. Tesla's original circuits, in contrast, rarely exceeded 100 kilohertz. His resonance tuning relied on intuition, sliding copper spheres, adjusting coil height, and listening for the faint whisper of corona discharge. He used spark gaps as crude oscillators, bursts of chaotic noise rather than steady waves. The new hardware, however, produced pure, stable sine waves. It could isolate the coil's natural frequency within 0.001% accuracy. When the automated sweep reached 700 kilohertz, the algorithm recognized a perfect impedance minimum, what it labeled a harmonic lock. Within microseconds, it increased dwell time to refine the measurement. That was enough. Inside the copper windings, energy began stacking in layers. Each successive pulse from the generator aligned precisely with the coil's own electrical rhythm. Voltage didn't merely rise, it compounded. In resonance, every cycle adds to the one before, like pushing a swing at the exact moment it reaches its peak. Within 20 milliseconds, the coil's terminal voltage leapt from a harmless 5V RMS to over 1.2 megavolts, climbing exponentially until the air itself could no longer contain the stress. Witnesses later compared the sound to a human scream drawn through metal. The air glowed pale violet. Sensors on the walls recorded a 12-microsecond burst of electromagnetic energy that saturated detectors up to 30 meters away. It was, as one engineer said, the day analog met algorithm, and the algorithm won. But the coil's behavior didn't stop at resonance. Hidden beneath the floor, a second network was awakening. One Tesla himself had designed more than a century earlier, waiting quietly for a modern source to feed it. Tesla believed the Earth itself was the ultimate conductor. In 1899, he wrote that he wanted to grip the planet so that the whole of this globe can quiver. To him, the ground was not an obstacle, but a pathway. His resonators always included long copper rods driven deep into the soil to complete the electrical loop. What the NYU engineers didn't realize was that their basement's ground grid, installed in 1968, shared continuity with those old rods still buried beneath the concrete. When the coil surged, that hidden network came alive. Current raced down through the ancient copper into the building's foundation rebar, through metal plumbing, and into the electrical bonding system that tied every outlet, pipe, and beam together. In an instant, the entire building became part of Tesla's circuit. The 12-foot arc that leapt to a shelving unit wasn't random. It was the visible endpoint of a feedback loop spanning hundreds of meters. The lab itself had become an antenna. Inductive coupling worsened the situation. The test cart holding the signal analyzer sat only 1 meter from the coil, its braided output cable draped casually over the edge, acting like a secondary winding. As the resonator's field strengthened, the cable absorbed part of that energy and fed it back into the generator's input stage. The feedback formed a closed resonant loop, coil to ground, to equipment, to coil again. With every pass, the amplitude doubled. Ambient radio frequency signals from nearby broadcast towers, FM at 88 to 108 MHz, AM around 700 kHz, added faint harmonics that fueled the coil's growing instability. Within seconds, the lab's air ionized. Sensors measured ozone concentrations at 0.15 parts per million, high enough to sting the eyes. Safety interlocks triggered, strobes flashed, power was cut, and the coil's arc finally collapsed. Yet, even disconnected from the mains, the readings revealed something remarkable. Residual voltage persisted for 22 seconds, gradually decaying. The building's ground network had stored energy like a massive capacitor. Tesla's dream of Earth-coupled resonance had come alive, unintentionally, in a 21st-century research lab. What made the event extraordinary wasn't a ghost in the machine. It was mathematics. A line of code and an AI algorithm had struck the one frequency Tesla could only approximate by ear. The testing platform responsible was an AI diagnostic suite built on TensorFlow 3.0, coded to identify optimal energy transfer points in complex circuits. Its learning model, trained on 40 million impedance profiles, could predict resonance with astonishing precision. Unlike a human technician who might hesitate near rising voltages, the program simply followed the math. When it reached 699.88 kHz, it flagged maximum coupling detected and held the signal steady. That steady tone, no jitter, no drift, was all the coil needed. Within 0.002 seconds, feedback loops began amplifying. Voltage doubled every microsecond, a geometric progression that no mechanical spark gap could ever sustain. The AI, unaware of danger, continued feeding energy until the protective relays tripped. Power logs later showed that in just 36 milliseconds, the coil's stored energy exceeded 1.9 megajoules, enough to vaporize copper if not vented through the air. The resulting 2 million-volt discharge was a purely mathematical accident. The AI had found perfection. Post-event analysis confirmed there was no hidden source, no perpetual motion. The mystery was resonance amplified by algorithmic timing. Tesla's coil, designed for rough tuning and hand adjustments, had never been meant to encounter digital precision. When old analog chaos met the cold logic of modern frequency control, physics took over. Safety systems, fortunately, proved their worth. Ceiling detectors sensed ionization density at 3 times 10 kg/m superscript 3, triggering automated evacuation. Breakers isolated the power bus within 8 seconds. The AI module itself was unharmed, but its logs recorded the moment of alignment, a perfect sine wave, zero phase error, amplitude rising until the data buffer overflowed. In the aftermath, scientists coined a new term, algorithmic resonance. It described what happens when a self-optimizing system discovers the exact conditions for runaway feedback faster than human oversight can intervene. Tesla had sought this precision for decades, and AI found it by accident in seconds. To outsiders, it looked like a haunting, an old machine screaming back to life. But to physicists, it was something far more instructive. Proof that even forgotten inventions can still teach and still burn when touched by the precision of today's tools. Beyond the mystery, speculation spiraled. Some witnesses spoke of a Tesla curse, others whispered of free energy rediscovered. But when physicists from MIT, Stanford, and the National Institute of Standards and Technology, NIST, reviewed the raw data, the verdict was unanimous. It was physics, not magic. The readings followed Maxwell's equations to the letter. The coil hadn't conjured power from the void, it had amplified it, exploiting resonance like a perfectly tuned instrument. At its heart, this was a story of constructive interference, the same principle that allows a singer to shatter glass or a bridge to sway with the wind. Every coil has a natural frequency. Tesla understood this intuitively in 1899, long before impedance spectroscopy existed. When an external signal matches that frequency, energy oscillates between magnetic and electric fields without dissipating, like a pendulum that never slows. The NYU coil, wound with 2.5 kilometers of copper wire, carried a natural frequency near 700 kilohertz. When the AI struck that exact note, each pulse reinforced the last. Within 40 milliseconds, the stored energy multiplied by a factor of 10, enough to ionize air across 12 feet and leap through the lab's steel frame. Tesla's analogy of pushing a child on a swing was no metaphor. Each electromagnetic oscillation added momentum when the timing was perfect. The AI, operating with nanosecond accuracy, became the perfect pusher. Meanwhile, the building's rebar and grounding grid reflected the wave back into the coil, preventing energy loss. In essence, the system formed a feedback cavity the size of a building. It wasn't free energy, but trapped energy, resonating until the air itself cracked under the stress. When investigators later overlaid voltage versus time, they found a near-perfect exponential curve. The system obeyed the classical resonance growth equation, V(T) equals V caret alpha T, where alpha represented the coupling coefficient. No mystical forces. No zero-point extraction. Just the precise alignment of frequencies Tesla could never fully stabilize by hand. The result was a vivid reminder that forgotten technologies still hold surprises when modern precision unlocks their full potential. Still, the shock wasn't only electrical, it reverberated through the scientific world. The incident forced laboratories, museums, and universities to reconsider the dormant devices sitting quietly in storage rooms. Research institutions around the world received the same urgent message. Legacy electromagnetic equipment may pose high-voltage hazards when energized, even at milliwatt levels. Within 2 weeks, the Smithsonian, Caltech Archives, and the Los Alamos Historical Foundation began auditing their collections. Coils, oscillators, and spark-gap transmitters from 1900 to 1950, devices that had remained untested for decades, were suddenly reclassified. No longer passive artifacts, they were now considered potential reactive devices. Many of these instruments had been built before standardized grounding existed. Their resonant circuits interacted with ambient RF noise and earth currents in unpredictable ways. Modern laboratories, dense with Wi-Fi routers, switching power supplies, and high-frequency electronics, create an electromagnetic soup far richer than Tesla's world ever contained. In such an environment, a stray connection, a loop of wire, or even a metal ventilation duct could form an unintentional coupling path. Follow-up simulations at Sandia National Laboratories confirmed the risk. Engineers demonstrated that a coil of Tesla's design could, in theory, self-excite if exposed to broadband emissions stronger than -20 dB per milliwatt at its resonant frequency. In practical terms, a nearby transmitter could wake it. The NYU surge also highlighted a growing collision between automation and legacy hardware. The AI had not broken any rules, it had simply followed its directive: maximize signal-to-noise ratio. What it lacked was historical caution. In response, institutions began embedding legacy-aware safeguards into automated testing systems. New code recognized potentially resonant geometries and limited dwell time near critical frequencies. In effect, humanity began teaching its machines how to respect the past. Museums followed suit. The Franklin Institute in Philadelphia and the Science Museum in London both suspended live demonstrations of vintage Tesla coils pending safety reviews. Curators who once thrilled visitors with crackling violet arcs began fitting display coils with dummy windings to prevent unintended feedback. The irony wasn't lost on anyone. A century after Tesla dreamed of global wireless power, his creations were again being classified as electrical hazards. Yet amid the caution came opportunity. The rediscovered coil forced engineers to reevaluate the craftsmanship of early technology. Tesla's winding ratios, insulation patterns, and geometric symmetry minimized energy loss more efficiently than some modern prototypes. Material scientists studying the copper purity, 99.97% conductivity grade, found it rivaled the industrial standards of 2025. Even the natural fiber insulation, treated with linseed oil and shellac, had preserved its dielectric integrity for nearly a century. Beyond safety protocols and engineering admiration, however, another revelation emerged, one that linked Tesla's vision directly to modern energy research. From past to future, his dream of a world without wires was being reborn under a new name: wireless energy transfer. In 1905, Tesla wrote that any point on Earth can draw power from the air itself. At the time, it was fantasy. But by 2025, the rediscovered coil reignited interest in that idea, not through mysticism, but through microwave physics and high-frequency resonance. Modern programs such as MIT's Wireless Power Initiative, NASA's Artemis Energy Group, and China's Zitianzhen University all touch Tesla's core principle: tuned circuits exchanging power through coupling. On small scales, this principle already powers electric vehicles inductively and charges medical implants via near-field resonance. On larger scales, it fuels the dream of space-based solar platforms transmitting gigawatts of energy to Earth via 2.45 GHz microwave beams. Tesla would have recognized the concept instantly, if not the technology. The NYU experiment proved, inadvertently, that even Tesla's century-old windings still embody the same physics driving today's most advanced systems. The combination of high-Q resonance, strong ground coupling, and synchronized frequency remains the foundation of all wireless power. Engineers studying the damaged coil's geometry found striking precision: a height of 1.8 meters, a 32-turn primary, and a spiral pitch ratio of 1 minute and 1.618 seconds, the golden ratio. Each proportion optimized field uniformity. What Tesla had intuited through intuition and experimentation, modern AI now confirmed through simulation. Beyond energy transfer, the event sparked new interest in directed energy defense systems, electromagnetic pulse mitigation, and underground power transmission. Agencies like DARPA and the European Space Agency launched studies into nonlinear resonant amplification, controlled versions of what had happened at NYU. In one sense, Tesla's ghost had joined the next century's arms race. Yet the scientific revival carried a philosophical one as well. Tesla believed resonance was more than physics. It was harmony, a synchronization of nature and invention. The NYU event reminded the world that progress does not come from abandoning the past, but from retuning it with care. Still, the lesson of Wardenclyffe's echo carries a warning, one that scientists now take very seriously. The surge in March 2025 was not supernatural. It was a bridge between centuries collapsing into one electric instant, a relic from 1901, a signal generator from 2025, and an AI coded in Python coming together in perfect phase alignment. The result was the most powerful unintended discharge ever produced by a single coil on Earth. No one was harmed, but the message was unmistakable. The past still hums with energy, waiting for the present to listen carefully. Investigators concluded that the event had occurred because of an algorithmic resonance lock. The AI had found a frequency Tesla could only approximate by ear, a note so precise it unlocked the coil's full potential. For the research team, it was both a revelation and a warning. In our pursuit of precision, they realized, we sometimes forget humility. A single line of code can now do what once took Tesla years of tuning, intuition, and experimentation. The danger isn't in discovery, it's in doing so without understanding what lies beneath. Since the incident, new global guidelines have reshaped laboratory practice. Any experiment involving legacy hardware must now include electromagnetic containment plans, frequency dwell limits, and machine learning fail-safes. Museums, too, are evolving. They now catalog not only what artifacts are, but how they behave under excitation. Engineers have begun to view historical devices as living systems, capable of response, even rebellion, when touched by the right frequency. But beneath the technical caution lies a deeper meaning. The NYU event didn't merely resurrect Tesla's technology, it revived his philosophy, that energy is everywhere, waiting to be harmonized. The same physics that unleashed a 12-foot lightning arc in a basement could, if mastered, beam power across oceans or sustain colonies on Mars. As Tesla once said, the line between danger and discovery is only a matter of tuning. The warning, then, is simple. When old rhythm meets new precision, expect sparks. Yet within those sparks lies a roadmap. If humanity can blend Tesla's imagination with today's precision, respect history while pushing its boundaries, the results could redefine how the world generates and uses energy. We don't have to repeat Tesla's mistakes. We can complete his work. As one researcher wrote in the post-incident summary, the coil didn't fail. It succeeded more perfectly than its creator ever imagined. We were the ones unprepared for it. The rediscovery of that crate, then, marked not an ending but a threshold between 1899 and 2025, between genius and algorithm, between resonance and chaos. The hum of the universe remains unchanged. Tesla once tried to make the world quiver. This time, for a heartbeat, it did. The past, it turns out, is never silent. It's merely waiting for the right frequency to speak again. When the lights came back on, the quantum computer's superconducting qubits were gone, fried in 0.04 seconds by an electromagnetic pulse from a machine older than Einstein's theory of relativity. Engineers watched as terabytes of entangled state data, weeks of computation, vanished into noise. Yet beyond the loss lay revelation. The old coil had simply obeyed the laws of resonance, achieving with analog harmony what algorithms could only simulate. It synchronized perfectly with its environment, amplifying energy through feedback until even shielded systems nearby felt the shock. For Tesla, resonance was never superstition. In 1899 at Colorado Springs, he wrote, "To understand the universe is to understand vibration." More than a century later, the event inside Google's lab proved he wasn't exaggerating. Modern machines strive for isolation, vacuum chambers, cryogenic filters, magnetic shielding, while Tesla built for connection, coupling his devices directly to the Earth itself. When those two philosophies collided, the past didn't crumble. It roared. Since that day, new safety codes have circled every research network. And never energize historical hardware near active quantum arrays. Never sweep blindly through unknown frequencies. And never forget that old physics can still find new power. What once destroyed a laboratory might one day power a city, if humanity learns control before curiosity strikes again. In the end, The story isn't about malfunction, it's about reflection. Tesla's vision and Google's ambition share the same pursuit, harnessing invisible energy through precision. One used sparks, the other qubits, but both sought the same resonance, the same truth. And when their frequencies aligned, time folded for an instant, and a century's worth of invention met its own echo. The future may run on quantum logic, but it still hums to Tesla's rhythm.